So have you seen the sphere in some context? The two sphere in R3. Have you seen it? You have not seen anywhere?
Yes, so we have seen that as a surface.
Right, in Carlson surface code, right?
Yes, sir.
Yeah, so is it a manifold?
Yes, so it's a two-dimensional manifold.
How do you show it? Do you have any idea?
Maybe a projection map into plane.
Projection maps into plane. Which projection map?
Geographic projection. We can like first. I mean, we can omit the North Pole and do it, and we can omit the South Pole. And
So where did you see the stereographic projection? Have you seen it in Carlson surfaces course?
yes, so we have seen that
Yes,
in
sir.
Carlson surfaces and analysis. Some analysis, but I don't remember.
Some analysis, I guess in complex analysis. Recently, is it?
No,
Sir,
so
I think
in
we
the
saw it
analysis
in
5 course.
analysis 3.
Oh, okay, yeah.
Yeah,
So
analysis 3.
models, yeah. Okay, so that is one thing. Can you tell me any other answer?
It's just coordinate-wise projection, just like what we did in S1.
Yeah, then what will be the open sets?
The hemisphere, and the lower hemisphere, and the side two hemispheres, right and left.
Right. So how many charts will be there?
4 charts.
4 charts. Okay, so let us see. We'll see that.
So
Then
that will cause problem with 2 points, right? If we have 4 charts,
Yeah.
then the front point and the back point.
right. So how many charts do we need?
So 6 charts.
Yeah. Right. So you need 6 charts. So since you are in R3, you need 6 charts. All right. So let me share it and let us try to see that two sphere is a manifold. Is everybody clear about stereographic projection? Or is there anybody who have questions about this or do not understand it properly? I'm asking because if you don't answer anything negatively, I might skip. So those who are confused or uh, who are not comfortable with it or have not seen it properly, just speak it up. Okay. So I suppose everybody knows it, right? So today is 17th. So we want to show first thing as the unit sphere in R3. So in its sphere, we denote it by S2, is a smooth manifold. So what is S2? S2 is nothing but X, Y, Z in R3 such that X square plus Y square plus Z square is equal to 1, right? So first thing is, so to show that we need to find an atlas, right? So you remember that once you have found an atlas, you have actually a different unique differential structure containing that atlas. So finding, to show something is a manifold, what you need to find is the atlas, or an atlas. So atlas may not be unique. There might be several atlases, but if you find one, that would be good enough, and that makes things much easier, because in a differentiable structure, you might have uncountably many charts, and showing that would have been very difficult. Atlas, you just have some minimal charts that does the job, that actually is good enough. So you have to show differentiable structure, what you need to find is an atlas. So atlas consists of collection of charts, which is in turn an open set and a map, right? So what are charts? So let me try to draw it. It's pretty bad. So if we look at the coordinate axis, let's call this x-axis. This is y-axis, and this one z-axis, right? So like the circle, we need to consider each of the half planes, each part of the open half planes, here open half spaces. For example, you intersect S2, with, let's say, with z greater than 0, right? So that is a half space, and so that would give you an open set. So that is an open set. So S2, let me write it. So U1 S2 intersection X, Y, Z in R3 such that Z greater than 0. So what is this? This is upper part. This is this part of the sphere, right? This part, right? This part of the here sphere. And this is an open subset. So this is an open subset in R3. Therefore, this will be an open subset. in the subspace topology of S2. All right. So this is U1. Similarly, you consider U2, and then of course, we need to give for phi1. Let me define here itself. So what will be phi1? Phi1 from U1 to R2, right? So this will be just the projection on z equal to 0 plane. All right. Is this fine, everybody? So how would you draw it? It's like this. So fix a point here. Just project it up. Project it down here. Some point here. So the image will be inside of this circle. Inside of this circle in R2. I mean, thinking z equal to 0, that gives you R2. So phi1 is phi1 xyz is x comma y. Does this make sense? Is it a 1-1 map? Is it a 1-1 map?
Sir, in U1, yes.
Yeah, of course, on U1. So similarly, we will define U2. So this is the first chart, and let me do here, and here let me divide the board into two parts. So now consider U2 as the following: S2 intersection x, y, z in R3 such that z is less than 0. All right. So what is this? This is the down part. This is this part. This part. All right. And here, what will be the map? Again, it will be projection to this. This is the great circle. So thinking this part, this one as great circle. So this one is great circle in xy plane. So this will be the projection. This will be the projection from here. Okay, so this should be phi2. So phi2 phi2 xyz. So phi2 is from U2 to into R2 is again x comma y. Right? So check phi2 is also 101. And similarly, you defined U3 to be S2 intersection xyz in R3 such that y greater than 0. And here phi2, phi3 from U3 to R2 by phi3 xyz is x comma z. All right. Similarly, you define U4 as S2 intersection x, y, z in R3 such that y is less than 0, and phi3 from phi4, from u4 to r2 by phi4 x y z is equal to x comma z. All right. Similarly, u5 s2 intersection x y z in r3. So you're dividing by one plane, right? One coordinate plane, such that x is greater than 0. Phi5 from u5 to r2 by phi5 xyz is y comma z. u6 s2 intersection xyz in r3 such that x is less than 0. Phi6 from u6 to r2 defined by phi6 xyz is equal to y comma z. So check each maps phi1, phi2, phi6 or the maps. The maps phi1, phi2, phi6 are homeomorphisms. All right. This is easy to check. Inverse is also very easy, right? So what would be the inverse of phi6? Yeah, can anybody tell me what will be the inverse of phi6?
Sir, given y and z,
Y
we can
comma
find
Yeah, given y and z.
x such that if you square all of them, x should be greater than 0, such that if you square all of them, it's equal to 1, and then take negative of that because it's in the bottom, it's in the left side. So minus x comma yz.
Right. That is the thing. Yes. So corresponding to each yz in a sphere, you can get at most 2 points, right? Corresponding to each yz in the plane R2, you can have 2x such that x comma y comma z lies in the sphere, right? Now in this case, since it is x greater than, so and the point is this x, and so it will be symmetric, reflection around the plane. So if x y z is there in the sphere, minus x y z is also there in the sphere. So spherical symmetry is something very interesting, right? So you reflect by any coordinate axis, it will be there in the sphere. So that's what we are using. So for every yz, of course not in whole of R2, right? So what will be the, it is in the disk. So image will be in the disk. For if you look at phi6 inverse, the image will be disk in R2. That means yz in R2 such that y square plus z square is less than 1. Right? You can't go beyond that, because that is the image of U6. Now corresponding to each point in the disk, unit disk, open unit disk, you can find a point, unique point x less than 0 such that x comma y comma z lies in the sphere. And that gives you the inverse. and inverse is clearly continuous. Right? Because you can write x. Yeah, I mean, you better write it properly. So given yz in unit disk, so I'll write that y comma z in R2 such that y square plus z square is less than 1. There exists a unique x such that x less than 0 and x, y, z lies in S2. How do you prove that? So claim is this. So yz is given, right? So let's write y naught z naught to make it's very simple. Now given y naught z naught, you want to find the point x, the points x such that x, y, z, x, y naught, z naught lies in the sphere. So you need to find, so we need to find the points x, y naught, z naught in S2 such x, y naught, z naught in R3. In R3 such that x square plus y naught square plus z naught square is 1. So which means x square is equal to 1 minus y naught square minus z naught square. So this means x is plus minus square root of 1 minus y naught square minus z naught square. So since we want negative, this one is less than 1, so that's perfectly fine. Square root is perfectly fine. So since we want x less than 0, therefore x is equal to minus 1 minus y naught square minus z naught square. So see, this is a smooth function. So this is the point. So phi inverse, phi6 inverse y comma z is minus minus 1 minus y naught square y square minus z square y comma z. Yeah, this is fine. Where it is defined? On y comma z in R2 such that y square plus z square is less than 1. Yeah, this is fine. Is this clear to everybody? So this is the way you need to show that this function is invertible, right? And inverse is also continuous because this is continuous and this is also continuous, right? So therefore this implies phi inverse, physics inverse is continuous, right? So one oneness gives you one inverse continuous, inverse gives you homeomorphism. So this implies phi inverse. Physics inverse is a homeomorphism. So I suggest you do it on your hand without looking at this calculation, so that you'll get to know this thing clearly. I mean, those who might be a little confused, but if you do the calculation on your hand, you'll be able to see it properly. All right. So each, what we get is each sorry, I should divide this first. So, so what we know is that uj, comma pj, j from 1 to 6 form a chart, right? Now, whether this collection gives you an atlas, right? So you consider f uj fj, j from 1 to 6. So question is whether f is an atlas, right? So what do you need to show for an atlas?
They cover the whole sphere.
Right. The first thing, union of uj. So what is the union of uj? It is whole of S2, right? Yeah. I mean each hub space you are looking at intersection with each hub space. So you have, suppose a ball is there here, and you divide in the middle and look at the hub, the one hub. Then you divide another one vertically, look at each of the hub, and similar things. That's definitely union is S2. And what is the second thing we need to check? Is okay.
C infinity compatibility.
Compatible.
Right. So you need to look at the transition functions, and you need to show that the transition functions are C infinity smooth. All right. So what are the transition functions? So second thing to show is the transition maps or function maps are smooth. All right. So how do you show this? So consider U1 intersection U2. So what is this set?
Empty.
Right. So this is empty. So there is no transition function here, which is vacuously true. Transition functions vacuously smooth. Right. So similarly, U3 intersection U4 is also empty. U5 intersection U6 is also empty. They do not have intersection. They are disjoint sets. Now you look at other things. So U1 intersection U3. So what is this set? S2 intersection. What is this set?
The z coordinate and y coordinate are greater than 0. The points like that.
Right. So X, Y, Z in R3 such that y coordinate is greater than 0, z coordinate is also greater than 0, right? And let us just find the first transition function at least, and then I'll stop. And I'll give you definitely more time on this after 3. Okay, so this is the intersection, and what is this image? So we looked at, let us draw the picture again. So we looked at This is one part, and we looked at, so this is x-axis, this is y-axis, and this is z-axis. So z greater than 0 gives you this one, this one, y greater than 0 gives you this one. This one. So this one, this part is the intersection. So this is the part we are interested in, right? So we need to look at first by P1, where does it go? See, y is greater than 0, z is also greater than 0. So P1, what was P1? P1 of x, y, z was x comma y, right? So this used to go, so this is the unit disk, let's say this is the center 0, and this is, since y is also greater than 0, so it will go to this portion. All right? Yeah, is this fine? So similarly here, under phi2, under phi3, so you go under phi3. So phi3, what was phi3? Phi3 xyz was x comma z, right? So this is also unit disk. Now in x and z coordinate, right? So here it is, this is x-axis and this is y-axis, and here it is x-axis and z-axis, right? So x is greater than 0 there, x is not greater than, z is greater than 0, right? So here this part, right? So now if you want to look at the inverse, so what will be it? So phi3 compose phi1 inverse. Let's say put as xy, x comma y. What will be it?
X comma root over 1 minus x square minus y square.
Oh, xy is there. You first go x comma, yeah, first go to x comma y comma root over 1 minus x square minus y square, right? Here. And then you go back by phi2. So this is, x will be there. And as you said, root over 1 minus x square minus y square will be there. So this is the map. Now we need to check, this is a diffeomorphism. So of course this is a homeomorphism, but this is also seen pretty smooth. So maybe I should give you an exercise here. So check. Oh, well, you don't need to check, it's clear. So it is clear that phi 3 compose phi1 inverse is C infinity smooth. Smooth, right? And exercise, check other transition maps. All right. Okay, so I'll stop here.